Now, armed with expansions of elementary functions, and of course their algebraic properties, which we know from high school, we can go ahead and study their numerical values. But first, what is a function? Function is a game of you give me a number, I'll give you a number. So according to some law, we have an x gives another number, f of x. So it's a mapping between two real numbers because we are limited to functions of a single real variable. Or we might say it is a function is a two-column table. Here I have x, here I have f of x, here I have a set of numbers and the corresponding numbers. Now, the reverse arrow is, of course, the inverse function. So, with those concepts in mind, we said that we have 27 elementary functions. These are the power function, then 6 trigonometric functions, 6 inverse trigonometric functions, then we have the logarithm and exponential functions, then we have the hyperbolic functions, 6 of them, and finally 6 inverse hyperbolic functions. In their numerical evaluation of functions, we realize that since it is a two-column table kind of structure, if we know how to evaluate a function, we also know how to evaluate the inverse function. So we can sort of eliminate the inverse functions. But before that, let us remember hyperbolic functions are nothing but the exponential function. Cosh is e to the x plus e to the minus x divided by 2. Kind of. And inverse hyperbolic functions are related to the logarithm. So these are redundant. Then if I know all the trigonometric functions backwards and forwards, that means I don't need a different method for inverse trigonometric functions. And one thing that comes to mind, what is the best way to express the power function? X to the a we can write as e to the ln x to the a power or e to the a ln x. So power function is also nothing but the exponential function when it comes to numerical properties. So these go away and we are really simplified into, let us say, 8. But not quite. If I know sine and cosine, the others are the other trigonometric functions are automatic, no problem. So let me say sine, cos, natural logarithm, and exponential. Now we saw that sine x for small values of x was x minus x cubed over 3 factorial, which is 6. X somewhat small in radian measure. So if x is really, really small, sine x and x are the same thing. Now I'll just give a formula. I will say sine of a degrees equals A for very small angles. But this A is degrees, but this x is in radians. How we convert x into degrees sort of thing? Well, the correspondence is 180 degrees is pi radians. Therefore, the degrees should be divided by 180 divided by pi, which is 57.3. So that's equals 1 radian. Now I'll do something sloppy. I'll say let us only divide A by 56, because 56 is a better number than 57. 57 is only divisible by 3 and 19, two prime numbers. 56 is somewhat better, 2, 4, 7. Now, is this good enough? It's good enough for small angles. How small? Well, let us say that A between 0 and 14, this is okay. Now, as A gets larger, of course, this term, the negative term, gets into effect. So sine x is somewhat smaller. So if I want a simple formula, I should take A and divide it with a somewhat larger number. 60 is a wonderful integer. It is divisible by nearly everything. And 15 degrees between 35 degrees. This is approximately okay. The rest is you use this information and all the algebraic properties of trigonometric functions to get everything you like. For example, so let's do an example. Arctangent 10 equals to what? Which means I want a angle theta so that tangent theta equals 10, which of course is sine theta over cosine theta. Now, if we are very sensitive about these things, let us say sine theta is u, and then cosine theta will be 1 minus u square. If I square both sides, 100 will equal to u square over 1 minus u square, or 100 equals 101 u square, or u equals to 100 over 101 square root, which is sine theta, which is very close. But if u square equals 100 over 101, then cosine, well, let's go into 2 steps. Sine square theta equals 100 over 101. That means cosine square theta equals 1 over 101. And that means cosine theta is approximately 1 over 10. Which makes sense because since trigonometric functions sine and cosine are limited in absolute value to values between 0 and 1, it is not possible for sine theta to be 10 and cosine theta to be 1 to get this number 10. We should have something like 1 over 0.1. So that makes sense. Our starting point, therefore, should be cosine theta is 0.1. You might have noticed I don't use approximately equal sign a lot. Everything is approximate in this lecture anyhow. So, cosine theta equals 0.1. But I can rewrite this as sine 90 degrees minus theta equals to cosine theta. Now, 90 minus theta is a small angle. Why? Because its sine is 0.1. If sine of some angle is 0.1, and that is a over 56, then the inside should be (5.6), because sine of degrees. Sine of 5.6 degrees, according to this formula, 5.6 divided by 56 is 0.1. So 90 degrees minus theta equals 5.6 degrees, or theta equals 84.4 degrees. That's our approximate answer. What is the exact answer? Well, 84.3 degrees. Who cares? So it's accurate enough as a first order calculation to have a feeling for numbers. Well, so much for trigonometric functions. With enough exercise, one can eliminate the unnecessary steps and get very close approximations to trigonometric functions. 3% accuracy without any calculators very quickly. Which brings us to the other immense project of exponentials and logarithms. Historically, ln x came much later with Euler. The original thing was the so-called Logx. This is to base 10. This is to base e. 10 is a nice number based on a biological accident because we have 10 fingers. E, of course, is something that arises from calculus. It is more sophisticated, and computer people use the base 2. In base 10, 10 is 10. In binary, 2 is written as 1, 0. Now, how do we calculate the logarithms? Let us first express that 10 to the power log x equals x. That's our basic thing. By the way, this is from early 17th century. People calculated logarithms of numbers. So let's have a table. N equals 1 is the trivial one. 3, 4, 5, 6, 7, 8, 9, and 10. Now, the logarithm of 1 is 0, because 10 to the 0 is 1. So let's do a 3 digits after the decimal point kind of thing, which brings us to 2. How about 2? You see, if I find 2, then 4 and 8 will be automatically calculated. Now, what is the approach to this? I want 2 to some power equals 10 to some other power. So how do I go about it? I go 2, 4, 8, 16, 32, 64, 128, 256, 512, and 1024. You see, of all these, 8 is close to a power of 10, namely 8 is nearly 10, but that's 20% off. On the other hand, this is only 2% or 2.4% off. So this is what I'll use. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Therefore, 2 to the 10 is 10 to the 3. So I go 10 times logarithm of 2 equals 3 times logarithm of 10. But logarithm of 10 is simply 1. Therefore, logarithm of 2 is 0.3. 0.3. Is this the exact value? No. To 3 significant figures after the decimal point, actually, there is a 1 here. But that's a very minor correction. Once I have that, as I told you before, 4 is easy because 4 is 2 times 2. So this is 0.602. And 8 is easy, 0.903. Another thing is simple. 5 is 10 divided by 2. So logarithm of 10, which of course is 1 followed by 3 zeros exactly. Then from 1, I will subtract 0.301. So logarithm of 5 will be 0.699. Quite an achievement. But 3 sort of stands out. Now you might think I will follow the same procedure and I will say, let's take the powers of 3. 3, 9, 27, 81, so on and so forth. Now, 9 is close to 10, but it's a 10% difference. Then when I look at 81, I realize that 81 is something I know because 81, which is basically 80, is 2 to the 3 times 10. So 81 is approximately 2 to the 3 times 10. So 3 to the 4th power equals 2 to the 3 times 10. So 4 times logarithm of 3 equals 3 times logarithm of 2 or logarithm of 8 plus logarithm of 10, which is 1. 1.903. So logarithm of 3 is 1.903 divided by 4. So that's 0.4 37 23 6. But the actual number is 7. So again, there is a minor correction in the third digit. Once I know 3, I know 6. Why? 2 times 3 is 6. So this is 0.778. 9 is just 3 square. So this is 0.954, which leaves us with 7. How are we going to do 7? Well, one thing comes to mind is 7 times 7 is 49, which is basically 50. So 7 squared is 10 times 5. So 2 times log 7 will equal to logarithm of 5, which is this, 0.699. A 10 from here, 1.699, but this is approximate anyhow, so let's call it 1.7. Therefore, 0.85 is a good enough thing. So these are the logarithms. But with logarithms to base 10, people did long calculations in a shortcut manner, very difficult divisions, so on and so forth, especially involving trigonometric functions. They had tables of trigonometric functions and their logarithms, so they could calculate star tables, so on and so forth, more conveniently. But then came calculus, and eventually we have to go to ln n. Now, what is the relationship between log n and ln n? Just like 10 to the log x equals to x, e to the ln x equals to x. So I may write e to the ln x equals 10 to the log x. Now, taking logarithms of both sides, or simply writing e as 10 to the log e to ln x, e to the ln x, I wrote just like this, equals 10 to the log x. So, log e times ln x equals logarithm of x, comparing the powers of 10. So my question is, what is logarithm of e? That's the coefficient that converts these. Well, for that, let's temporarily remember what e is, or the expansion of e to the x. It was 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, so on and so forth. How about x equals to 1? When x equals to 1, e will equal to 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, so on and so forth. So let's do it. 1, 3 zeros. Another one, 3 zeros. Then 1 over 2. 0.500. Then 1 over 3 factorial, which means I'll divide this by 3. So 167. Then I'll divide this by 4. 0, 4, 1. Then I'll divide this by 5. 8. 40 divided by 8. Then I'll divide this by 6. Well, this is good enough as a start. So 7, 1, 7, and 2. 2.717. The actual value is 2.718 and other integers, 2, 8, so on and so forth. So E is basically, for our purposes, 2.7. Approximately. So how do you find the logarithm of that? Well, 2.7 is 3 to the third power divided by 10. Therefore, log E will be 3 times log 3 minus 1. Well, 0.43 is good enough. How about 1 over log E, 1 over 0.43. This is, if you do the arithmetic, is 2.3. So my formula is ln x is 2.3 times log x. Let's use less significant figures. For 1, I'll have 0, as usual. How about ln 2? I will multiply 2.3 by 0.3, 0.69. Well, let's be generous and call it 0.7. Then 4 is 1.4, 6 is to be determined later, 8 is 2.1. 10 we know is 2.3. Now once I know 10 and I know 2, I can find 5, which is 1.6, because 5 is 10 divided by 2. How about 3? If you do the multiplication, 0.477 times 2.3, it is approximately 1.1. So 6 is 2 times 3, 1.8. And 9 is 2.2. 7 again is missing. We can do a direct multiplication, or we can do an interpolation. You see, at first I have a big jump, a 0.7 jump, then 0.4, then 0.3, 0.2, 0.2, but here in this region 0.1. So a an interpolation, the average between these, 1.95 for the natural logarithm of 7 makes sense. Now using these, we can do lots of interesting calculations. But first, what is the formal definition of E? How did we come about this? Well, E is actually a limit of 1 plus a very small number to a very large number. U goes to infinity. So it is one of the indeterminate forms, 1 to infinity. So how does one go about this? If you do it, you will get the expansion we talked about using binomial theorem, so on and so forth. But the basic idea is rewriting this 1 plus a very small number to 1 over delta equals E, where delta is very, very small. So this is the basis of doing lots of interesting calculations. Compound interest problems or population increase problems. Suppose thousand years ago, a couple settle and they raise a family. This is a compound interest problem. You see, rate of population increase is a variable. It depends a lot on health conditions, economic conditions, and many other factors, including the climate. Now, for example, in Turkey, the lowest was between the years 1940 and 1945, the Second World War years. The rate of population increase was 1%. Then, in 60 to 65 interval, it rose to 3%. Now it's 1.4%, something like that. So, okay, just for the argument, let's say 1.4% rate of population increase. So, population now would be population at 0, which is just 2 people, then 1.014 to 1000 power. Now, 1.4%, if you 0.014 is approximately 70. So I can write this as 2 times 1.014 to 70 to 1000 over 70. Well, this is 2. This is E, 1 plus a small number to 1 over that number, this thing, to 100 over 7. Well, that's e to the 14. This is piece of 1000. E to the 14, how do you evaluate this? Well, we first try to find out how many 2.3s are there in 14. So 14 divided by 2.3. Well, how about 6? Well, there is 6 and change. Because 6 times 2.3 is 8, 13.8. So this is 2, then 10 to the 6, and then that remaining e to the 0.2. Well, e to the 0.2 is roughly 1.2. Remember, e to a small number is 1 plus that small number. 1.2 times 2, 2.4. So this is 2.4 million. If, on the other hand, we do a more dramatic calculation, a certain Bishop Usher consulted religious books and decided that the earth was founded at something like 4000 BC. So let us say 6,000 years ago, a couple starts a family. Let us assume the same rate, R equals to 1.4%. So the population today will be 6,000 years later. The original couple times 1.014 to 6,000, which I'll write as 70, then 6,000 divided by 70. So this is 2 e to the 600 divided by 7. So which is 8. Six, approximately. Now, how many 2.3s are there? Well, 86 divided by 2.3. This is 30 something. 35. It's close enough. So this is 2 10 to the 35. Now that population is actually would be more massive than the Earth itself. If I remember correctly, the mass of the Earth is something like 10 to the 24 kilograms. Well, 50 kilograms per person. It is much, much, much larger than that. Probably this is heavier than the sun itself. So that's the power of the exponential function. Well, one final advice when doing numerical calculations, skill helps. A good collection of functional properties in one's mind also helps. But the most important thing is courage. You should not be afraid to make mistakes. Do an approximation, come up with the result, look at that result critically, and if it makes sense, then do a double check, triple check, so on and so forth, even use a computer. If it doesn't make sense, you should have an instinct to be able to go back and correct yourself. Where did you go wrong? Now, there are places where the series expansions are useful, but there are places that series expansions are not useful at all. The most obvious example is 1.1 plus 1 over 2, 1 over 3, 1 over 4, the harmonic series. If you sum the first billion terms using a computer, this will be something like the logarithm of a billion, natural logarithm of a billion. So it will be 9 times 2.3. It will be something like 25. Therefore, there are places where computers will mislead you. You should also know the analytical expressions. Somewhere in your mind you should remember that the harmonic series diverges. So my recommendation is test yourself. There are 27 elementary functions. Choose an arbitrary function, choose an arbitrary argument, try to evaluate it. Given enough practice, one masters these things. Okay.